How many class, sir?
So, am I audible?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. So, in the last class, we have completed Coulomb's law. Like we did Coulomb's law in vector form. We also discussed superposition principle. We have done some numericals on superposition principle also. So, Coulomb's law is after Coulomb's law. The next topic is electric field. Basically, the next is electric field. Okay, if we talk about force, then to exert force in a system, you should have at least two charges. If you have a single charge, then this single charge will not exert force. To exert force, you should have at least two charges. At least two charges are required to exert force. So you can say that electric force is the property of at least two charges. If you have one charge, then you will not feel any force. For force, you need at least two charges. Next is electric field. Sorry. So after force, the next topic is electric field. So what is electric field? Electric field is the space around charge. Space, by definition, the electric field is space around charge in which its electrical properties can be experienced. Electrical properties can be experienced. So this is the technical bookish definition of electric field, can be experienced. But before starting with electric fields, let's discuss something about field in general. Have you heard about any other field than electric field? Yes, Amalia. Have you heard about any other field than electric field? No. Okay. Fatma, have you heard about any other field than electric field? Okay. Magnetic field. Magnetic field is one example. Mariam, have you heard about any other field than electric field and magnetic field? I think there was one field in the last class 11 syllabus also. Uh, okay, now you can unmute yourself. Yes, just tell me, have you heard about any other field than electric field?
So gravitational field.
Gravitational field. So the various examples of fields are electric field, magnetic field, gravitational field. These are some examples of field. Just a second, I'm having some technical issues. Just 1 second. I'm just checking my microphone. Yes. So you must have heard about two other type of field. One is gravitational field, another is magnetic field. So in general in physics we have three types of field. One is electric field, another is magnetic field, another is gravitational field. Now, can you just tell me why the concept of field is important? Why we use the concept of field here? Why we use the concept of gravitational field? Why we use the concept of magnetic field? See, to go deep into the topic that why we need the concept of field, we first know what are the two types of forces we have. The forces that you have around can be divided into two types. Forces can be contact force, or your forces can be non-contact in nature. So these are the two types of forces. Your forces could be contact forces, or your forces could be non-contact forces. So contact forces are basically those forces which acts when two bodies are in contact. And for non-contact force, physical contact is non-important. One example of contact force is normal reaction. Means when this hand becomes in contact with the second hand, then only these two hands can exert normal force, normal reaction on each other. Another example of non-contact force is tension. Tension is basically the force which string exert on a body. For a string or a wire to exert force on a body, wire and body should be in contact. So we have two types of forces. One is contact, another is non-contact force. For contact force, physical contact is important. Like if I want, I'm repeating again, if I want both of my hand to exert force over each other, then these two hands should be in contact. Then only they can exert force over each other. Then you have another type of forces which are known as non-contact force. One example of non-contact force is magnetic force. If I take a north pole of a magnet here and I take a south pole of a magnet here, there is no contact in between them, but north and south will attract each other. This is an example of non-contact force. Another example of non-contact force, say you have a north pole and a north pole, there is no contact between them, but they can repel each other. So they repel each other by a force. Again, for that force, the physical interaction, physical contact is not required. So is these two type of forces are clear, contact and non-contact forces?
Yes.
Okay,
Yes.
just tell me, electric force is contact or non-contact force?
Non-contact.
Electrical force is non-contact
Non-contact.
force. If you have a positive charge and a negative charge, then these two charges can attract each other. For attraction, you don't need any contact in between them. It's a non-contact force. Now, to explain non-contact force, you need concept of field. We basically use the concept of field in physics to explain non-contact force. So I'm writing it here as a next point. To explain non-contact force, concept of field is required. We need concept of field to explain non-contact forces. So see how field explain non-contact force. Let's start with electric field only. So you have a charge plus Q. And there is this charge plus Q again. This capital Q and small q. This capital Q will repel this small q. Now I want to define a mechanism through which this capital Q can exert force on small q. And that mechanism is through field. So when we explain force through field, what we do is we first say that this is a charge, a source charge, which is generating electric field. So you have a source charge here. This source charge will generate a field here. You can consider this field as a form of wave. So you have a charge, it generates a field here. And then this is test charge. When I place a test charge in this field, then this field will exert force on the test charge. So it's basically a two-step process. In the first step, source charge will generate field. In the second step, this field will exert force on the test charge. So when we talk about force, it's a two-step process always. One charge will generate field. That field will travel up to the second charge, and then this field will exert force on the test charge. So using field, we have explained how this Q is experiencing force due to capital Q. And this field travel with the speed of light. Electric field travel with the speed of light. Electric field travel with speed of light. So this is how a charge experience force in terms of field. So this was, through this term, I was explaining force on the test charge Q. Now, if I want to explain the force on capital Q, now I need force on capital Q. Mariam, which charge will generate field? I want force on capital Q.
The small charge will generate the
Small
field.
charge, small q, very good. So small q will generate field. Now this field will exert force on capital Q, and this capital Q will experience a force. So this is how it works. One charge generate fields, then that field interact with another charge and experience a force. So this is the concept of field. So what is field? It's basically the space around a charge. If I take a charge plus q, then there is a space around this plus q charge. In this space, its electrical properties exist, its influence exists. So this is the space in which its electrical influence exists. That space is known as electric field. If I place any other charge in this space, let's say I place a charge plus q in this space, then capital Q can exert a force over this small q. But if I put a charge small q outside this space, then small q cannot experience force. The small q can only experience force if it is placed inside this region. So you can say that electric field is the region of influence, the region in which the electrical properties of this particular charge exist now. Is it clear, everyone, this introduction of electric field?
Yes,
Yes, sir.
sir.
Because from now onwards, we will always explain quantities in terms of field. We will even express force in terms of field. And one more thing. What do you think? Electric field is a property of a single charge or at least two charges? To generate field, you need at least one charge, minimum one charge, or more than one charge?
Minimum 2 charge.
Minimum 2 charges.
One.
One
To
charge.
generate field, you need one charge. But to experience force, you need another charge. For field, you need just one charge. So electric field is property of at least one charge. So if you have a single charge, then that charge will generate field. So you have force, which is property of at least two charges, and you have field, which is property of a single charge. So Ahmed, which quantity is more fundamental? Is it field which is more fundamental or force which is more fundamental?
Force.
Force. Well, I guess the property of a single charge should be more fundamental. Property of a single charge should be more fundamental than the property of two charges. Because if you have a single charge, then you don't have force. For force, you need one extra charge. So the quantity that depends on one extra charge cannot be fundamental. The more fundamental quantity is field. When we study electrostatics or when we study magnetism, field is more fundamental than force. First charge generate fields, then that field will exert force on another charge. Just note it down and tell me if you have any doubt in it. Because for the next 1 week at least, we will be studying electric field only. So if you have any doubt regarding what is electric field, we can discuss it now. Amalia, Fatma, Sania, is it clear?
Yes, sir. Yes.
Yes, sir.
Okay. Just note it down. Then we'll see how to calculate field.
So can you explain the last part?
Yes. This electric field is property of at least one charge?
Yeah, the circle one.
Yeah, just circle one, okay.
Yeah.
So you have a charge capital Q. Huh? Around this charge capital Q, there is a space in which its electrical properties exist. Means there is a space in which its field exists. So the space around within which the electrical properties of a charge exist, that space is known as electric field. Electrical properties exist, that means if I put a charge within this space, then this capital Q can exert force over this charge. But if I put charge outside this space, then this small q will not experience any force. This will experience force only if it is placed inside this space. This space or this region of influence is known as electric field. Is it clear now?
Yes, sir, it's clear.
Okay, now I have few questions. Okay. Say I have, let's say I have this pen. I have this pen. I rub this pen. Now, after rubbing, this pen must have gets charged. If this pen is charged, then this pen should generate that electric field. It should generate some electric field. Now, can you guess up to what region this field can exist? Means this field will exist only within this classroom only, or the field can exist throughout the universe. What do you think? The field of this charge is in a finite region or an infinite region?
A
Infinite.
finite region.
Finite.
Infinite region.
Infinite.
Okay. So you're getting what I'm asking, huh?
Yes, sir.
This is generating some field. That field can exist only within a certain region, maybe in this classroom only, or this field can exist throughout the universe up to infinity only.
That theoretically it is infinite, but it has a limit for itself.
Yeah. So as Ahmed is saying, theoretically the field can exist up to infinity, but here infinity have a different meaning. Here infinity does not means the infinity that you have studied in maths. Okay, I will come to the issue of infinity now. The first thing is, if you have a charge, then the field of that charge will exist in a certain region only, in a certain finite region only. It's very practically you can see that this charge can exert force through a finite distance only. So its field exists in a certain region only. Field cannot exist throughout the universe. That's the one thing. Now, when I say that field exists in a finite region only, then the question comes that usually people says that the range of electric force is infinite. I'm mixing two things. I'm saying that if I have a charge, that charge may generate some field, and that field will exist in a finite region only. Field cannot exist throughout the universe. It will exist in a finite region only. But when you study about electric force, you will study that range of the electric force is infinite. Now, this have contradiction. The two statements have contradiction. On the one hand, I'm saying that field exists in a certain region only. And on the other hand, I'm saying the range of electric force is infinite. That means electric field can exist up to infinity. Now, the issue is the concept of infinity. In maths, we have various types of infinities. Okay, can you name some different types of infinities? Like, okay, I'm giving you example of various types of infinity. This is number line, this is 0, this is 1, this is 2, this is 3, and this is plus infinite. So this is one infinity. If I go to the left hand side, -1, -2, -3, minus infinite. This is another infinity. Then, can you tell me the number of decimals in between 0 and 1? How many decimals are there in between 0 and 1?
Infinite.
Infinite.
So in between 0 and 1, you again have infinite decimals. So that's your third type of infinite. Now, if I take one number, like I take 0.5. So between 0 and 0.5, how many infinites are possible? Sorry, how many decimals are possible?
Infinite.
Finite.
Infinite again. So one more type of infinite. Now, can you guess how many types of infinites we have?
Infinite.
Infinite types of infinites.
So we have infinite types of infinite. So what does infinite exactly means in physics? When we say that range of electric force is infinite, then what does we mean? We mean this infinite, or this bigger infinite? So are you getting my point? Are you getting the paradox, the conflict? When
Yes,
I'm
sir.
saying that the
Yes, sir.
field, the range of the field is finite, and then I'm saying that the electric field can exist up to infinity. So the issue is with this infinity only, we have various types of infinities basically. When we say that the range of electric force is up to infinity, then by infinity we means infinity is the region in which the effect of charge vanish. Like if I take a room, I take a charge, and I say the effect of this charge exists well inside the room, but as I move outside the room, the electrical effect of this charge reduce to zero. So the region outside this room, I will call this region as infinity, and the region inside the room is finite region. So infinity doesn't mean thousands and millions of kilometers. Infinity simply means, when we talk about electric force, the region in which electric force reduce to zero. So infinity means region in which electric force reduce to zero. This is how we understand infinity in physics, or in context to electric force. So if I'm saying that I just rub this pen gets charged, this is generating some electric field, then that electric field is existing only within the room only. So the region within the room is finite region, and the region outside this room will become infinity. Is it clear about the range of electric force?
Yes,
Yes,
sir.
sir.
Note it down. Then we'll start some calculations. If you still have any doubt about electric field, we can discuss it. In your syllabus, you will study about various types of field. You will study about electric field, then you will study about magnetic field in very much detail. So the concept of field should be very clear. Okay. So this was some basic definitions of electric field. So electric field is the region in which electrical properties of a charge exist. Now we have to measure the strength of that region. We basically have to measure at what point electric field is strong and at what point field is weaker. So the quantity that we measure to decide the strength of electric field is known as electric field strength. Electric field strength, or electric field intensity, or electric flux density. Electric field strength, electric field intensity, or electric flux density. This is the quantity that we will measure. So this is charge Q. plus Q. I want to measure the electric field over this point A only. Amalia, to measure this field, do we need another charge or we can measure field using this single charge only? Amalia, to measure field, do we need another charge? We need at least two charges, or through one charge we can measure field?
Through one charge.
One charge, because field is the property of a single charge. So this capital Q should generate a field here, E. Though this field is a property of single charge only, but for theoretically to measure field, we will take help of a charge, and that charge is known as test charge. Basically what happens is field is not visible. If you take a comb, you run that comb through your hair, the comb becomes charged. That means that comb is generating some electric field. And that comb is generating electric field. This you can verify by putting that comb near some pieces of paper. If comb can pick the piece of paper, that means field of comb is traveling up to that piece of paper. But that field is not visible. So to decide whether field exists or not at a particular point, what we do is we put a test charge over that point. If that test charge could experience a force, if that test charge could experience an attractive or a repulsive force, you can observe this force. You can, due to this force, this test charge could move. So just by seeing that this test charge is experiencing a force, you can conclude that field exists over this point A. I'm repeating the entire discussion again. You have a charge capital Q. I call this charge as source charge because this charge is generating some electric field. I want to calculate the field over this of this source charge over point A. But the issue is the field, although field is generated by a source charge only, but field is not visible. We cannot see field through our naked eyes. So what we do is we put a test charge over here. That charge is visible. If this test charge experience a force, then through that force you can conclude that electric field exists over this point, because electric field is basically exerting this force only. So just by seeing the motion of this charge, you can conclude, okay, field exists over this point. So just to decide whether field exists or not, I'm using this test charge only. But I'm not calculating field of test charge, I'm calculating field of source charge only. So electric force Fe experienced by test charge small q due to field of source charge capital Q. So the field of source charge capital Q will generate some field. So we can define this electric field of source charge as electric field of source charge E is equal to, the definition is, this is force experienced by the test charge divided by the magnitude of test charge, provided limit Q tends to 0. I will come to this point why I'm writing limit Q tends to 0. But this is the definition of field. To measure field, it's very straightforward thing. What we do is we put a test charge over the point. We calculate force over the test charge that you can calculate using Coulomb's law. Then divide this point force by the test charge. Whatever you get is your electric field only. Now, why I'm using this limit Q tends to 0, this we will discuss. But tell me, instead of this limit Q tends to 0, is it clear E is F by Q? This is definition.
Yes, sir.
Yes, sir.
Abdullah, this E is the field of which charge? Small q or capital Q?
So capital Q.
Capital Q. Sania, which charge experience this Fe force? capital Q, small q?
Capital Q.
Which charge? Small q, na?
Small Q.
Who is exerting force on a small q charge? If a small q is experiencing force, then someone must be exerting this force. Who is exerting this force on small q?
Capital Q.
This
Force
capital.
charge.
Capital Q. I would say not directly capital Q, but the field of capital Q. The field of capital Q E is exerting force on small q, and that is Fe now. So this is how we define field now. But there is one small issue. The small issue is to calculate this force, capital Q should be at rest. Capital Q should be at rest. Capital Q should not move. But in this case, capital Q can move. Amalia, can you just tell me why this capital Q will move? When I take two charges, then capital Q can move. Which force is responsible for the motion of capital Q, Amalia?
The electric field. So I'm not sure.
Just listen question again. I'm saying you have two charges, capital Q and small q. Small q is moving due to electric force exerted by capital Q. Now I'm asking, this capital Q can also move. Which force may be responsible for the motion of capital Q? Just try once again.
Small q.
Small q, yes. Yes, exactly. Small q can exert force on capital Q. Now, both are positive charges. So the small q can repel this capital Q. When small q will repel this capital Q will move. When this capital Q would move, that means capital Q will experience a force. So capital Q can experience force due to this small q only. But if this capital Q moves, then we cannot use this formula. We can use this formula only if capital Q is at rest. So to keep this capital Q at rest, we have two methods. One is we can fix this capital Q. What we can do is we put some glue and fix this capital Q on the surface so that this capital Q cannot move. This is one method. By the way, it's a very vague method. Another method is, see who is repelling this capital Q? Small q is repelling this capital Q. If I take small q very, very small, then the force will be small. If I take small q to be negligibly small, then the force will be negligibly small. And q, small q, then will not be able to repel this capital Q. I'm repeating again. To use this relation, your capital Q should be at rest. To make this capital Q at rest, small q should be a very small charge so that force exerted by small q on capital Q is negligible. That's why I'm putting this limit here, that limit q tends to 0, that small q is infinitesimal small charge. So I'm putting,
Yes, sir.
yes, Ahmed.
Can we instead put like same normal on the opposite side so that the charges cancel out?
Okay, you want to put this charge over here. Yeah, one charge here, huh?
Yes, sir.
No, basically when you are writing this force, you're writing force of small q only. We're writing force of small q only. When we calculate field, we calculate force due to one charge only. So while calculating this field, you cannot consider force due to this charge. You cannot consider force due to this charge. That's the issue. You will consider one charge at a time, so that force exerted by small q is negligible, and hence capital Q cannot move. This is the reason why we are using this limit q tends to 0, so that q is negligibly small, force is negligibly small, and it will not move. See, Ahmed, whatever you are saying, na, if I put a cap Q1, then this Q will not move. Physically, that's fine. That's not an issue. But mathematically, when we write field of a charge, then we take force of another charge and divide that force by the magnitude of another charge. If you take force of two charges, then in this denominator, you should incorporate the two charges, which is not possible. That's why I'm not asking you to include this charge here. Physically, it won't. Physically, it will solve this issue, but mathematically, you cannot write it. That's why I'm not considering it. Now, yes, tell me, is this definition clear?
Yes, sir.
It's
Yes,
simply
sir.
force experienced by test charge divided by the magnitude of test charge. Okay, note it down, then move further. Now, can I change the slide?
Yes, sir.
Yes.
Yes, sir.
Now, what type of quantity is electric field? Electric field is a vector. Is a vector. Its direction is same as that of force experienced by test charge. Its direction is same as that of force experienced by test charge. Next. Its SI unit is, see, the SI unit of field is, what is field? Field is force divided by charge. So SI unit of force is Newton, charge is Coulomb. So SI unit is Newton per Coulomb. There is one more unit which we write volt per meter. So I cannot explain from where this volt per meter comes here at this moment. We will discuss it when move on to chapter number 2. So these are the two SI units, Newton per Coulomb or volt per meter. Okay, after this, there is one definition of electric field, and the definition is E is limit Q tends to 0, it's F by Q. Now, if I put Q equal to 1 plus 1 Coulomb, then I can write that E is equal to limit Q tends to 0, it's F divided by 1. So, or I can write that E, since we have substituted the value of, there is no Q here, like this is limit Q tends to 0, F. There is no Q here now. So we can remove this limit and you will get E is equal to F. So if I take a test charge of 1 Coulomb, then the force exerted by the test charge will be exactly equal to the field. So we can say that electric field, this is the definition of field. Electric field at a point can also be defined as force experienced by unit. Now, when I'm writing field, that means electric field strength or electric field intensity. Casually, we write electric field strength as electric field only, experienced by unit positive discharge. So electric field at a point can be defined as the force experienced by a unit positive test charge only. This is electric field. Okay, just note it down, then we'll move on to the next topic. Just note it down. Then move on to the next topic. It's okay.
Done, sir.
It's okay. Written, everyone?
Yes, sir.
Yes,
Okay.
sir.
Yes, sir.
Okay. So solve these questions. A test charge is a simple formula based numerical, but just it will check the understanding of the your basic concept of electric field. Huh? You have a test charge of 10 raised to the power minus 3 coulomb. It experience a force of, and all will report the answer in chat room. Huh? It will experience a force of, let's say, 10 raised to the power 2 Newton due to field of a source charge. Calculate the magnitude of field. Yes, solve it now. It's hardly a one line, two line calculation. Calculate and report your answer in chat room. I muted the mic. Just report your answer in chat room. Yes, Noor is correct. What about the rest? 7, you 7 are still. I open the mic, but please don't just answer in chat room only. Noor is correct. Ahmed is correct. Abdullah, you're making some mistake. Mariam is correct. 4. 4 still left. No, Sania. See, use this relation. This relation. So you have everything. You have F, you have Q. Yes, Abdullah, now you are correct. Fatma, Ahmad,
Yes, sir.
Shahzada, your answer. Yes,
Sai
Amalia.
gave.
Okay, Ahmad gave. Yes, yes, Ahmad is correct. Shahzada, your answer.
Yes, sir.
You're doing this calculation?
Yes, sir.
Okay, just choose Fat and report your answer in chat room. Fatma, your answer is not correct. Amalia is correct. Abdullah is correct. Sania is wrong. Sania, just repeat these calculations again. Sania and Fatma. Shazad, it should not take that much of time. It's straight calculation. शहजादा रोजा लग रहा है. Okay, yes, that's correct. 10 raised power 5. So C is a straightforward formula based thing. Your electric field is F by Q. F is 10 raised power 2. Test charge is 10 raised power minus 3. It comes out to be 10 raised power 5 Newton per coulomb now. Sania and Fatma, is it correct now?
Yes, sir.
Yes, sir.
Sure. Okay. So if you have force and test charge, then you can easily calculate field. Just take the ratio. Now, when we write this relation, like E is limit Q tends to 0 F by Q, this formula is valid for all type of charges. This source charge could be a point charge, it could be a rod, it could be a ring, this could be of charge of any type. So this is valid for all type of charges. It's valid for all types of charges. Now we need formula, we need relations for a point charge only. So I'm deriving a relation for electric field. Electric field for a point charge only. So what we do is we take a source charge. It's your source charge. You're supposed to calculate field over of this source charge. And this source charge is a point charge. The body on which the charge is distributed is just a point. It's a point charge. And at a separation R from this source charge, you're supposed to calculate field. You're supposed to calculate field over this point. Now, to calculate field over this point, what we do is we put a test charge here. The separation is R. So this is your source. This is your test charge. Source charge will repel this test charge with a force Fe. So electric force on test charge F is equal to 1 over 4 pi epsilon naught. It's QQ by R square. This is equation number 1. So this is the electric force acting on the test charge. 1 over 4 pi epsilon naught QQ by R square. And who will exert this electric force? The electric field of the source charge. So this electric field of the source charge will exert this force. So electric field we can do one more thing. This is the magnitude. For the complete vector form, I'm using a unit vector r cap. You all know what is unit vector, and we have already used unit vector to specify the direction while doing Coulomb's law in vector form. Now for electric force of source charge, not electric force, electric field of source charge. Yes, Sania, if I have force, I know test charge, then how could you calculate field? How would you calculate field using force and test charge?
F by test charge.
F by test charge. Good. So that's limit Q tends to 0. This is force experienced by the test charge divided by the magnitude of test charge. So the electric field is limit Q tends to 0. It's 1 by Q into F. F is 1 over 4 pi epsilon naught. It's Q by R square into R cap. This Q will cancel this Q. this E is limit Q tends to 0, 1 over 4 pi epsilon naught. It's Q by R square into R cap. This is the expression of field. Now, since there is no small q, so there's no point in writing this limit. We can remove this limit and we will be left with electric field is 1 over 4 pi epsilon naught q over r square only. So this is the expression of electric field due to a source charge. And this is how we calculate field for a point charge only. But remember, this is valid only for point charge. If you have a rod, or if you, let's say if I take this pen, I charge this pen somehow, this pen will generate electric field, but I cannot calculate that electric field using this expression. This is valid only for a point charge, 1 over 4 pi epsilon naught q by r square. If I write the magnitude of field, then magnitude of field is just 1 over 4 pi epsilon naught. It's q by r square only. Next, we can easily decide the direction of the field. For direction, just remember this sentence that for positive charge, field is away from the charge. For negative charge, field is towards the charge. So if you have a positive charge, then the direction of field is away from the charge. But if you have a negative charge, then the direction of field is towards the charge. So this is plus q. Direction of field is away from the charge. And this is minus q. Direction of field is towards the charge. So this is how we can decide the direction of field for a positive charge or for a negative charge. This is how we decide the direction of field for positive charge or for a negative charge. For positive charge, it is away from the charge. For negative charge, it is towards the charge. So if I put a charge, let's say a charge of plus 2 coulomb here, and I need direction of field over this point. Shahzada, can you tell me the direction of field over this point? Field due to this plus 2. In which direction this field will act? Upwards, downwards, rightwards, leftwards?
Upward.
Upwards, away from the charge. If I calculate it here, then what would be the direction?
Downwards.
Downwards. Sania, if I calculate direction of field over this point, then what would be the direction? Right, left?
Left.
Left.
Hmm.
This is away from the charge or towards the charge, this direction?
Towards the charge.
Towards the charge. And what about this?
Away from the charge.
This is away from the charge. Will act in right hand side direction. Over this point, what should be the direction of field, Sania?
Right.
Left.
Left.
If I draw right, then this is towards the charge. And for positive charge, this is away from
Away.
the charge. So if I take this negative charge, minus 2 coulomb, Ahmed, what is the direction of field over this point?
Downwards.
Downwards. Abdullah, what is the direction of field over this point due to minus 2?
Left.
Leftwards. Noor, direction of field over this point?
So towards right.
Right. And Noor, what about direction of field over this point?
It's upwards.
It's upwards. Perfect. So these are the directions of field for positive as well as negative charge. Okay, tell me one more thing. Fatma, this expression of field that I have written here, 1 over 4 pi epsilon naught q by r square, this is valid for any medium or for a specific medium? Fatma.
Specific medium.
Which medium? Which specific medium?
I don't remember.
When I write epsilon naught, yes, someone was telling.
Air.
Air or vacuum. When I write
Vacuum.
epsilon naught, that means air or vacuum. Now, if I want to change medium, if charge is placed in any other medium, then free space. When I say free space, that means air or vacuum. Placed in any other medium. Now, if I place charge in any other medium than free space, then what will be the expression of force? Shahzada, what change are you expecting in the expression?
Epsilon naught it will change.
Epsilon naught will change. How it will change?
Not instead of that, which medium is there that will apply.
We can use dielectric constant also. This is easier.
Yeah, we can
What
use
you
that.
are saying is not wrong, but usually you will not find the value of epsilon of different medium. You will rather have dielectric constant. So
Okay.
this is the dielectric constant of that medium. Okay, so next I'm writing one basic, very basic formula based question. I have a charge of plus 10 coulomb at origin. Calculate electric field at a point charge. At a point A, the coordinates of point A are 200, not 2300 meter. I need both magnitude as well as direction of field. I need magnitude and direction of field. Solve it. And report your answer in proper unit vectors, j cap, k cap, I cap, minus I cap, whatever unit vector you think is appropriate in this situation. Have you written it, this whole derivation?
Yes, sir.
Everyone?
Yes.
Yes, sir.
This one? Everyone have written it?
Yes, sir.
Yes, sir. Yes, yes.
Okay, solve this numerical. Just straight formula based thing. And again, when you calculate it, just write your answer in chat room. So very, very small calculation. Why are you taking so much time? It's not that long.
Point.
Chat room only. Noor, you're doing some silly mistake. You're doing some silly mistake. No, Abdullah, 1 over 4 pi epsilon naught is 9 into 10 raised power 9. This whole term is 9 into 10 raised power 9. Sania, you're again making some mistake. Amalia, you and Noor are making exactly same mistake. You both have missed the square of r. You're not doing square of r. 9 into 10 raised power 9. 1 over 4 pi epsilon naught is 9 into 10 raised power 9. Abdullah. Yes, Ahmad, you are right. Ahmad, just put proper unit vector for the direction. Ahmad, your magnitude is exactly correct. Just put proper unit vector for direction, for the sake of direction. Yes, you are right. What about the rest? Mariam, sorry.
Yes, I'm doing.
No, Abdullah, you're again making mistakes. No. Shazada, Sania. Fatma, your magnitude is correct. Also mention the direction. Sania, again you are wrong. You're again making mistakes in calculations. No, Abdullah, no, wrong. Yes, yes, Fatma, direction is correct. Ahmed, yes, Ahmed is right. Shazada,
Yes, sir, 1 minute.
yes, Mariam, now you are correct. Yes, Amalia, magnitude is right. Amalia and Mariam also mentioned the direction, huh? What's the direction of the force? Noor, check your calculations. Yes, Mariam, this is right. Just use proper unit vectors, I cap, j cap, k cap. Yes, Shahzada, your magnitude is right. So almost everyone is correct. See, you have a charge of plus 10 coulomb. This is placed at the origin. Huh? This is point A. Its coordinate is 300 meter. Means from the origin, this is at a separation of 3 meter. You're supposed to calculate field at this point. So to calculate field at this point, no, 300. Okay, you are taking 200. Then it's fine. So E is 1 over 4 pi epsilon naught. Okay, then it's right, Abdullah. Then it's correct. Q by R square. Now we just substitute the values. 1 over 4 pi epsilon naught is 9 into 10 raised power 9. Q is 10. R is 3. So that's 3 square. 3 square is 9. Gets cancelled out. So your field is 10 raised to the power 10 Newton per coulomb. It's 10 raised power 9 multiplied by 10. It's 10 raised power 10. Now, if we talk about the direction of the field, the charge is positive. So the direction of field is away from the charge. So the unit vector that we will use here is I cap, 10 raised power 10 I cap Newton per coulomb. Everyone clear now?
Yes, sir.
Yes,
Yes.
sir.
Okay. Note it down. Then we will
Certain.
do some graphs. Huh? Then we'll discuss graphs. Have we discussed graph in the last class? No.
Yes.
No, sir.
Well, let's discuss some basics of graph.
So we can write it like this.
Uh,
We have to
no,
write
Ahmed,
direct
no, Ahmed.
numbers.
Usually we write unit after the direction. After the quantity is completed, then we write unit. I cap is a part of quantity. So we write I cap before unit. Unit is at the end. Okay. Okay, let's discuss some basics of graphs. Some basics of graph from class 10th and class 11. Then I will move on to numericals of electrostat, which use the concept of graph. So I'm not discussing graph in detail. I'm just picking only those topics that you will use in your class 12 syllabus. But yes, I'm picking those topics from the scratch. So if you have not done graph in class 11, then also it won't be an issue. So what are graphs? Graphs are basically pictorial. You can say it's a pictorial representation of a function. You can say that graphs are pictorial representation of a function. those who don't have maths can understand function as equation. If I give you an equation, then what that equation represents can be shown in the form of picture if we plot the graph. For example, if I write this equation that y is equal to x square. Sania, can you tell me if I increase the value of x, then what will happen with y? Y will also increase or it can decrease? Sania.
It will increase. It will decrease.
Decrease, okay. Shahzada, if I increase x, then what will happen with y?
So it can increase.
It will increase. It will always increase. See, this is x square. If I take x equal to 1, then your y is 1 square, which is 1. If I take x equal to 2, then your y will be 2 square, which is equal to 4. So this equation or this function is giving you an information that if you increase this independent variable, then your dependent variable y will also increase. If you increase one variable, then another variable will also increase. This is the information that we are getting from this graph, getting from this equation. The same information you can get from the graph of this equation. If I plot x versus y graph for this equation, the shape of the graph will be this. From this graph, it's very clear that if you are increasing x to the right hand side, then your y is increasing. See, you are increasing x, your y is going upwards. As we go upwards, then y increases. As we go rightwards, your x increases. So if I'm increasing x, your y is also increasing. So this graph is telling you the same story which this equation is telling you. But the equation shows things mathematically and the graph shows in the form of picture. So from this graph, is it clear for everyone that on increasing x, y is also increasing?
Yes, sir.
Okay, if I'm drawing this graph, I'm drawing this graph. Mariam, can you tell me on increasing x, what is happening with y?
Y is decreasing.
Y is decreasing. See, when I'm increasing x, what happened to y? Y is decreasing. So this graph basically tells a story. To interpret that story from the equation, we have some set of rules. So here I'm not discussing all the rules of the graph theory. I'm just discussing some rules which you will use in class 12 syllabus. So the first thing is you can have various shapes of the graph. This particular shape is known as parabola. We call this as a parabolic graph. This particular shape is known as hyperbola. This particular shape is known as straight line. So just by looking at this equation, you have to decide what would be the shape of your graph. So the shape of the graph depends upon the type of equation. So the first shape that of the graph that we can have is straight line graph. Straight line graph. For straight line graph, your equation should be linear. You should have a linear equation. If your equation is linear, then your graph will be straight line. Means if you have y which is proportional to x. When I say linear, that means both x and y will have single power. If both have single power, then your equation is linear and your graph will be a straight line graph. This is for a linear equation. But if you don't have a linear equation and if you have a quadratic equation, if we have a quadratic equation, then the shape of your graph is parabolic. We have various types of parabola, but the type of parabola that we will use in class 12 syllabus is this only. For this shape, the equation should be quadratic. Quadratic means y is proportional to x square. And the third type of shape that you will usually encounter in your first 4 chapters is the shape hyperbola. This shape basically. For hyperbola shape, your equation should be of this form. Y is inversely proportional to x. y is inversely proportional to x square, y is inversely proportional to x cube. So these are the various types of equations that one can have for a hyperbola. So this is x, this is y, this is the shape of the graph. For all equations, 1 by x, 1 by x square, 1 by x cube, shape is same. The only difference is the steepness. 1 by x is less steep, like this one. 1 by x square is steeper, 1 by x cube is steeper than the 1 by x square curve. So these are the three type of graphs that you will encounter in class 12 syllabus. Straight line, for straight line, check whether your equation is linear or not. For parabolic, check whether your equation is quadratic or not. For hyperbola, check its inverse form of equation. Yes, tell me, is it clear, these three types of graphs?
Yes,
Yes,
sir.
sir.
Yes, sir.
Good. Okay, just note it down. Then we will plot graph for Coulomb's law, graph for electric field. Just by looking at the equation, you have to decide whether your equation is linear, quadratic, or hyperbola. Then you can decide the shape of the graph.
Done, sir.
Okay. Can I change the slide?
Yes, sir.
Yes, sir.
Mm, plot first part. F versus R graph for Coulomb's law. Second, F versus 1 by R square graph for Coulomb's law. I need these two graphs. One is F versus R, another is F versus 1 by R square graph. First graph. So if I write Coulomb's law, F is 1 over 4 pi epsilon naught Q by R square. So F is inversely proportional to R square. Shahzada, out of the three shapes, which shape is for this particular equation?
Hyperbola.
Hyperbola. So if you plot F versus R graph, this is R and this is F, then the shape would be hyperbola. Your graph would be hyperbola. Second part. Now he's asking about 1 by R square, F versus 1 by R square, not R. So, you know, the formula is 1 over 4 pi epsilon naught Q by R square. So you have to compare F with 1 by R square, not with R. So what you can do is just write 1 by R square as X. When you substitute this value here, we will get F is 1 over 4 pi epsilon naught, its Q multiplied by X. So you will see that F is directly proportional to X. F is directly proportional to X. That means, so what should be the shape of the graph?
Linear shape.
Linear.
Parabola.
No, no, not parabola. F is proportional to X. For parabola, it should be square.
Straight line.
Straight line. I'm putting, you need one F versus 1 by R square. Although you can check it directly, F is directly proportional to 1 by R square. F is inversely proportional to R, but with 1 by R square, it's directly proportional. So we can put just 1 by R square equal to X. F is proportional to X now. So this is F, this is X. The shape of the graph will be straight line. A straight line. So these are the two important type of graph for Coulomb's law. One is F versus R, another is F versus 1 by R square. Is it clear?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, just note it down. Then we'll plot one more graph. What are the Asar timings there?
I said 3,
3,
3:15.
3:15.
Yes, sir.
So do you need gap for Asar?
So we will just delay for 15 minutes, right? So you can just continue the class.
So 3:30, na? Okay. So the timing is 3:15 around, na?
Yes,
It's
sir.
3:09.
3:09. So okay, I will leave around 3:20, 3:15, na?
I said the azan is at 3:09, but
Azan
prayer
mein,
will be like around 3:15 to 3:20.
so I can leave around 3:20, yeah, or
Yes, sir.
3:15. Okay, so written.
Yes, sir.
Amalia, you got disconnected. Just take screenshot of this slide. I think you have missed this slide. Yes, Amalia. Taking screenshot of this slide
Yes, sir. Done.
and also the screenshot of this slide.
Yes, sir.
Okay. Next question is plot electric field versus R graph for a point charge. This is the expression of field for a point charge, 1 over 4 pi epsilon naught. It's Q by R square. Fatma, can you check the relation between E and R? What type of relation is this, linear, quadratic, or inverse? E and R. Yes, Fatma. What type of relation is this between E and R? Linear, quadratic, or whatever? No,
I think quadratic.
The quadratic.
quadratic. See, this is R square. This is inverse. Quadratic is this. E is proportional to R square. This is quadratic. It's not quadratic. This is inverse. Okay, Fatma? Quadratic means R square is in numerator, not in denominator. So this is inverse relation. So Mariam, what should be the shape of graph for this particular type of
It will
relation?
be hyperbolic.
Hyperbolic. So this is R, this is E, this will be the shape of the graph. Your graph will be hyperbolic. Remember, it will not touch the x-axis. It will become parallel to x-axis. Note it down. So these were the two shape of the graph for the electric field and force. Tell me when you have written, I'll change the slide. So, okay. So till now, the expression of field that we did is for a point charge only, for a single point charge only. So if you have a point charge, then field is 1 over 4 pi epsilon naught Q by R square. But if you have more than one point charge, like if you have 10 point charges, then to calculate field, you have to use superposition principle. So the next is superposition principle. It's same as that of force, but instead of force, now we will be adding electric field. It's superposition principle. Just give me 1 minute. Okay. So for superposition principle, we will use superposition principle for a system having more than 1 point charge. If you have a system which have more than 1 point charge, then we can use superposition principle. So superposition principle says for a system having n interacting point charges, net field at a point is vector sum of field due to individual charges. So you have various charges. You want to calculate field at a point due to all of these charges. So what we will do, we will calculate field due to each of the individual charge and then just add them up vectorically. It's like force. Earlier we were taking force due to each charge and we were adding it vectorically. Now instead of force, we will take charges only. So you have one charge Q1 here. You have another charge Q2 here. You have another charge Q3 here. They all could be positive or it could be combination of positive and negative charge. You want to calculate field over here. So this for plus Q1 is the direction of field. For plus Q2, this will be the direction of field. And for plus Q3, this will be the direction of field. So this is E1. This is E2. And this is E3. Or if I write this as nth charge, then it will be En. So what we do here is we take field due to individual charges and then just add them up vectorically. So the net field is E1 plus E2 En. We will take field due to each of the individual charge and then just keep on adding it vectorically. This is the superposition principle for electric field. Just note it down. Then we will start calculation for superposition principle. We'll do some numericals based on superposition principle.
Yes, sir, done.
Okay. Okay, in numericals of superposition principle, we will use a term which is known as neutral point. We will use a term which is known as neutral point. See, what is neutral point? Neutral point is basically that point at which field of individual charges cancel each other. So the point at which the electric field of individual charges cancel each other is known as neutral point. So you can have two charges and at a certain very special point, the electric field of these two individual charges can cancel each other. So the point at which field cancels is neutral point. So point at which electric field of individual charges cancels. So the point at which the electric field of individual charges cancels is known as neutral point. Just note this definition, then we will do one numerical to calculate the position of neutral point.
Done.
So the question says you have two charges, huh? You have two charges plus E and plus 4E are placed at separation, let's say, at what point on the line joining the two charges net field is 0. Basically, is asking about the neutral point. See, the calculations are very straightforward. It's like the equilibrium question that we did in the last class. So you have a charge plus 4E. You have a charge plus 4E. Let's say I call this is the neutral point. So let's name this as charge A. Name this as charge B. This charge A will generate field here, and that is EA. Charge B will generate field here, which is EB. Net field at neutral point is the sum of field due to the two charges. Net field at neutral point is the sum of field due to charge A and field due to charge B. This is equal to 0. No, both the fields are in opposite direction, so we can directly subtract them, that EA minus EB is equal to 0. The separation between both the charges is A. So we can say that this separation is X and this will be A minus X. So you can say that EA will be equal to EB. Amalia, what is the formula to calculate EA, electric field due to this charge over this point at a separation X? How would you mathematically calculate field due to this charge E over point N?
1 by 4 pi
Hmm.
epsilon 0
Mhm.
E for E
E bar.
by X squared.
Yeah, not 4E. You're not calculating force, you're calculating field. Huh? So it will depend on E only. Similarly, you can write EB, which is 1 over 4 pi epsilon naught. It's 4E over its A minus X whole square. So this 1 over 4 pi epsilon naught will cancel this 1 over 4 pi epsilon naught. E will cancel this E. We are left with 1 by X square is equal to 4 by A minus X square. Next, what we can do is we can take square roots on both the sides. So we can write this as 1 by X is 2 by A minus X. Next, we can just cross multiply them. 3x. So your X is A by 3. Means from at a separation A by 3 from this charge plus E, net field is 0. So you can conclude one more important result from here. Okay, just tell me, out of E and 4E, which one is the smaller? Obviously, E is smaller.
E.
And neutral point is at a separation A by 3 from the smaller charge, and this is at a separation 2A by 3. If I substitute X here, A by 3, then it will be 2A by 3. This is at a separation of 2A by 3 plus from plus 4E. So we can conclude that neutral point lies close to smaller charge. We can conclude that neutral point lies very close to a smaller charge. So if you have two charges, then your neutral point will lie close to smaller charge. So if I take a charge of plus 1 coulomb and plus 3 coulomb, then neutral point will lie near this plus 1 coulomb charge. It will always lie near charge having smaller magnitude. Just note it down. That was question on 2-point charges. Then we will do question on 4-point charges.
Certain.
Okay. So everyone have written?
Yes, sir.
Yes, sir.
Okay, can you guess the position of the neutral point if both the charges are equal?
Center, midpoint.
Center.
Midpoint. If both the charges are equal, then we call system as symmetrical. We'll call that system has symmetry. If all the charges in your system are equal and they are placed at equal separation with respect to each other, then you would say that your system has symmetry. Your system is symmetrical. And for symmetrical systems, we have a general result, and that general result says that electric field at the center of symmetrical system is 0. So if you have a symmetrical system, then electric field at the center of that symmetrical system is always 0. Take example of symmetrical system. The simplest symmetrical system is the system of 2-point charges. We have a charge Q. We have another charge Q. This is the center. This separation is A and this is A. So at the center of symmetrical system, field is 0. If I talk about 3-point charges, then we have the symmetrical system as the vertices of an equilateral triangle. So electric field at this point N is 0. So if I take equilateral triangle, I put one charge on the vertices of equilateral triangle. Each vertex have one charge. Then at the center O, the field is 0. If I take 4 charges, then what should be the shape of the system?
Square.
If we have 4 charges, the system would be a square. This is the center, O. You can say that field at O is 0. If I take 5 charges, then
Pentagon.
Pentagon.
pentagon. Just keep on increasing the number of charges. You will be having polygons of various sides, and field at the center is always 0. So these are usually 1 marker questions. This is Q, this is Q, this is Q, this is Q, this is center O. Electric field at the center O is 0. And if I take infinite charges, then it will be a ring. For 6 charges, it will be a hexagon. For infinite charges, it will be a ring. Electric field at the center of the ring will be 0. Just note it down. So if you have a symmetrical system, that electric field at the center of that symmetrical system is always 0. We will prove one of these results. Just tell me when you have written.
Done, sir.
Done, sir.
Certain.
So can you show the previous slide?
Yes, 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 yes.
Yes, sir. Thank you.
So the question is, you have a square. On every vertex of the square, you have a charge. Let's say you have a charge plus q here. You have a charge plus 2q here. You have, let's say, 2q here. And you have another charge minus q here. Let's put minus q here. Okay, tell me, is this symmetrical system?
No, sir.
No, sir.
No, sir.
Yes, it's not a symmetrical system. Huh? All charges are not equal. It's not symmetrical. So electric field at the center cannot be zero. Each side of the square is zero. So you're supposed to calculate electric field at the center. Now to calculate this field, we will need superposition principle. Okay, just note it down this question, then we will start. Okay. So this would be your homework, but I'm giving you hint to calculate it. Each of this individual charge like A, B, C, D, each of this individual charge will generate electric field at the center. Like charge at A will generate field at the center, EA. Charge at B will generate field at the center, that's EB. Charge at C will generate field at the center, EC. And charge at D will generate field at the center, that is ED. Each of this individual charge will generate field at the center. Now to calculate this field at the center, you will need this separation. This separation AO. For AO, you can use this fact that AO is just half of the diagonal.
Sir,
Yes.
sir, for minus q, it will attract, right?
Minus Q will attract, right? Yes, yes. And similarly, this EC. Thank you. So this negative charge, see, it's the negative. So direction of field will be towards the charge. That's EC. This D is negative. So direction of field is towards D. That's ED. Now to calculate these fields, you will need this AO separation. That's AC by 2. How much is AC? For AC, you can use Pythagoras. It's a right angle triangle. This ADC is a right angle triangle. So for AC, you can write it's A square plus A square divided by 2. So you can write that AO is root over 2A square by 2. So that will be A by root 2. So this AO, BO, CO, and DO all are equal, which is equal to A by root 2. So once you have these separations, you can calculate field due to individual charge. And the last step would be you have to add them up vectorically. Okay, so I should leave now. Just note this hint. And I will need one extra class because on Wednesday, on every day, 15 minutes will loss. So I will take a class just to compensate those 50 minutes. 15 minutes. Maybe on Friday, on Saturday, we can have one more class.
So can you explain this part?
Yeah. This is basically this one. This AO is just the half of AC. So for AC, I'm doing this like Pythagoras theorem.
No, sir,
This,
the root one.
yeah, this A
Root.
square plus A square is root over 2A square. Then you can take this A outside the root. You will be left with A root 2 divided by 2.
Okay, sir.
Okay, then if I cancel them out, then this will be A by root 2. That's A by root 2. Okay. Yes, Abdullah, class is over. Okay, I will update in the group one more timings for one more day. That day may be on Friday or on Saturday. Just let me discuss with Nishkarsh. I will inform in the group about the next class. We have one class on Wednesday and Monday. That's it. But we will have one more extra class, maybe on Friday or on Saturday. That I will discuss on the group. Okay, let's stop here. We'll continue this in the next class.